Morning, dear student. In today's lecture, we will discuss the important point regarding to the amino acid and protein is the protein ligand interaction. So, how this protein molecule interact with different ligands and what are the different types of this protein ligand interactions? So, we will discuss in detail. So, let us discuss the first important point is that the types of protein and ligand interactions. So, the first one, the type of protein ligand interaction. Protein ligand interaction. So, total there is a four types of protein ligand interaction. The first one is reversible binding. Reversible binding. Reversible binding of protein. Reversible binding of protein to ligand. Reversible binding of protein to a ligand, and we are very much familiar with this type, that is reversible binding of protein to a ligand. The best example of this type protein ligand interaction is the interaction of oxygen with hemoglobin and myoglobin. So we are very much familiar with this interaction, that is interaction of O2 with hemoglobin and myoglobin with HB and MB. So we are very much familiar with this interaction of oxygen with hemoglobin and myoglobin. So we are very much familiar with this myoglobin and hemoglobin. Both are the oxygen carrier. We can say that hemoglobin and myoglobin is the protein. So what is the function of this hemoglobin? It will transport the oxygen from lungs to the different tissues. And what is the function of this myoglobin? It will store this oxygen. So this hemoglobin and myoglobins are the heme protein. It contain the heme as a prosthetic group. They are the heme protein, and it will interact with oxygen. So without oxygen, it is called, for example, if you consider this hemoglobin and myoglobin, they are again classified into two types. One is deoxyhemoglobin and one is oxyhemoglobin. Deoxy means without oxygen. When oxygen is not bind with hemoglobin, then it is considered as a deoxyhemoglobin. When oxygen is bind with this hemoglobin, then it is considered as the oxyhemoglobin. So we will discuss later on, but at least you should know when you consider a reversible binding of protein to a ligand, you must keep in mind the interaction of oxygen with hemoglobin and myoglobin. Again, this myoglobin is a monomer while this hemoglobin is a tetramer. So we already discussed the tertiary and quaternary structure of the protein. So myoglobin, it is your tertiary structure of the protein, and hemoglobin is your quaternary structure of the protein. So this is the interaction of oxygen with hemoglobin and myoglobin is considered as a reversible binding. Again, the second important type of this protein ligand interaction is the allosteric protein interaction. Allosteric protein ligand interaction. Allosteric protein ligand interactions. So what is this allosteric protein ligand interaction? An allosteric protein ligand interaction is one in which the binding of a ligand to one site of a protein affects the binding properties of another site of the same protein. So you should remember, whatever the binding of a ligand to a protein which affects the another site of the protein. So we can say that an allosteric protein is one in which binding of a ligand to one site. So we can write here binding of a ligand to one site of a protein one site of a protein affects the binding properties of another another site of same protein same protein. For example, again we discuss the same example, that is interaction of oxygen with hemoglobin and myoglobin. For example, let us consider the hemoglobin. So with deoxy form of hemoglobin without oxygen, whatever the deoxy form of hemoglobin, in which it consists of a heme as a prosthetic unit, it contains Fe second. Fe is present, metal ion is present, and it is in +2 oxidation state. Without oxygen, if you consider, there is a lot of interaction between this protein molecule. We already discussed this interaction, and due to this, the deoxy form of hemoglobin is a tense state. We can consider it is as T state. It is not relaxed, so it is a tense state because lot of interaction is there, and whatever the metal ion, it is not fit into this cavity of this prosthetic group, and therefore if you consider the deoxy form of hemoglobin, it is a tense state. What happens when oxygen is bind, or we can say that whatever the Fe is present in a deoxyhemoglobin, it is in high spin state. So we are again very much familiar with high spin complexes and low spin complexes. So whenever we consider a deoxy form of hemoglobin, Fe is present in high spin state, and when oxygen is bind with this heme protein, or we can consider it is when it bind with Fe, the heme part of the protein molecule, hemoglobin protein molecule, then what happen, the high spin Fe second, it is converted into low spin Fe second, and the properties are changed. So this is the allosteric interaction. So binding of a ligand to one site of a protein affects the binding properties of another site of a same protein. So this high spin complexes is converted into low spin complexes. Again we can say that the square pyramidal complexes is converted into square planar complexes. So we'll discuss later on all this interaction. So you should remember the allosteric protein. Another example is there, but we will discuss it later. The third important type of this protein ligand interaction is the cooperative binding. Cooperative binding between protein and ligand, cooperative binding. So we are again very much familiar with this cooperative effect. So cooperative binding between protein and ligand. So we know that this hemoglobin, it is your tetramer, so it contains 4 polypeptide chain. When one oxygen molecule, when attached to this one polypeptide chain or one subunit, then there is a cooperative effect. So then the hemoglobin molecule shows cooperative effect. When the second molecule of oxygen, when it is forms the bond with or interact with this protein molecule, the heme part of the protein molecule, then the rate of the reaction is increases. So you should remember what is the cooperative. Cooperative means the rate of the reaction is very fast. As the first molecule bind, the rate is very slow, but when the second molecule of oxygen, when it binds with the hemoglobin molecule, then the rate of the reaction or the binding of oxygen to hemoglobin is increases. Similarly, when the third molecule and the fourth molecule of oxygen is attached to this hemoglobin protein molecule, then the rate is very fast, and this effect is considered as a cooperative effect, and it is considered as a cooperative binding between protein and ligands. So binding of one molecule increases the rate of reaction or increases the speed of the reaction, we can say that. So this is regarding to the cooperative binding between the protein and ligand. Again, the fourth important type is the complementary binding. complementary binding between protein and ligand, between protein and ligand. So you should remember these four type of interaction between protein and ligand, that is reversible binding of protein to a ligand, then allosteric protein, then cooperative binding, and the fourth one is the complementary binding between protein and ligand. So let us discuss the first type of interaction, that is the reversible binding of protein to a ligand. First one, that is reversible reversible binding reversible binding of protein to ligand. So for this interaction we consider a oxygen binding protein. The example is oxygen binding protein. Oxygen binding protein, that is your hemoglobin, or we can consider it is your myoglobin. Oxygen binding protein, that is your hemoglobin and myoglobin. Before discussing the interaction, protein ligand interaction of oxygen with hemoglobin and myoglobin, we will discuss, because what is this hemoglobin and myoglobin? If you consider, this is the protein. The hemoglobin and myoglobin is a protein, but it is a heme protein. So hemoglobin means, if you consider this hemoglobin, then it is made up by two components. One is heme and second is a globular part of the protein. So heme as a prosthetic group, and the second one is a globular part of the protein, So this hemoglobin, it is a protein, it is an oxygen carrier protein, but it is made up by two important constituent. One is heme and second is globular part of the protein. So it consists of the heme unit, it is known as prosthetic group. So let's discuss some important point regarding to this heme as a prosthetic group, and then we will discuss the interaction. So if you consider the iron porphyrin is referred as heme as a prosthetic group. So the interaction with Fe, the interaction of porphyrin ring with Fe, it is considered as a heme. So porphyrin is there and metal ion is Fe, then this interaction, the interaction of Fe with porphyrin, it is considered as a heme. Heme is a prosthetic group. So this heme, it is a prosthetic group, heme, it is your prosthetic group of hemoglobin and myoglobin. The framework of heme is derived from porphyrin. So you should remember the second point. The framework of heme, that is your iron porphyrin ring, it is derived from, the framework of heme is derived from porphyrin, porphyrin. So what is this porphyrin? So you should remember the first one, that is porphyrin, then porphyrin, okay, then it is heme unit, and then it is act as a prosthetic group, okay. So what is this porphyrin. Porphyrin, an unsubstituted tetrapyrrole ring connected at the alpha carbon by methylidine linkages. So what is this porphyrin? It is an unsubstituted tetrapyrrole connected at the alpha carbon by methylidine linkage or methine linkage. So what is this porphyrin? It is not porphyrin. Porphyrin, 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 an unsubstituted tetrapyrrole connected at the alpha carbon by methine linkage. Then it is considered as a porphyrin. So let us discuss the structure of this porphyrin. This porphyrin, so if you consider the structure, double bond is there, double bond is here. We cannot write this. This is your NH. Again, this is your NH. Nitrogen is there. So if you consider, this is the structure of porphyrin. It is unsubstituted. So there is no any substituent on this system or porphyrin ring. If you consider when the substitution, let us discuss the position. This is carbon number 1, this is carbon number 2, this is 3, 4, then it is 5, 6, then it is 7 and 8. If we count the double bond in this system, then total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. So total 11 double bond is there. 11 double bond is there. It is unsubstituted, therefore it is considered as a porphyrin. When the substitution on 8 pyrrole position on porphyrin ring produce, if you consider when there is a substitution on 8 pyrrole position, then the porphyrin ring produces porphyrin ring. If you consider this is the 8th position, whenever there is any substituent is attached, so substituent is attached on 8th position of this pyrrole ring, pyrrole of this porphyrin, then this porphyrin it is converted into porphyrin. This porphyrin it is converted into porphyrin ring. Different substitution on this porphyrin ring at the 8th pyrrole position produces protoporphyrin, so which is the heme unit. So you should remember unsubstitution ring system, it is considered as a porphyrin. Whenever there is a substitution, then it is considered as a porphyrin ring. So we are very much interested into the porphyrin ring. So this is your porphyrin when there is a substitution. For example, if in the same ring, if there is a substituent such as methyl group is there at 8th position, again methyl group is there at first position, then alkene is there at second position, ch double bond ch2, again fourth position ch double bond ch2 is there, third position it contain methyl group, fifth position it also contain methyl group, then at the sixth position it contain the aspartate. So it is not aspartate, it is glutamate, ch2 minus residue. Again the seventh position is ch2 co minus residue, and then this ring is considered as a porphyrin ring. Porphyrin ring, this porphyrin ring, if you consider when this porphyrin ring donate to proton, when this ring donate to proton to H plus ion, then it convert into dianion form, that is it having a -2 charge. And when this negatively charged porphyrin ring interact with Fe, then there is a formation of Fe porphyrin complex, and this Fe porphyrin complex is considered as a heme part of the hemoglobin. So you should remember. So porphyrin, the unsubstituted tetrapyrrole ring linked by methine linkage, carbon-carbon double bond linkage, total 11 double bond is there. Whenever there is a substitution, then the porphyrin is converted into porphyrin. Again, when this porphyrin ring, the 2 nitrogen, when it donates 2 hydrogen, then this porphyrin it is converted into -2, it having a -2 charge, and this ring, this porphyrin ring which having -2 charge, it will interact with your Fe, and there is a formation of Fe porphyrin complex. So in this case you can write here, so the 2 hydrogen it is replaced, and here the Fe it will bind with this 4 nitrogen. Fe is bind with this 4 nitrogen, and the whole complex, this whole complex of Fe and this porphyrin, it is considered as the heme part of the hemoglobin. It is a heme part of the hemoglobin. So if you consider the Fe is attached to 4 nitrogen, actually the complex is octahedral, so it also having a 2 site. The one site, if you consider the fifth site of this iron porphyrin ring or Fe is attached to the nitrogen of histidine. The fifth site it is occupied by the amino acid residue, that is N-histidine, nitrogen of histidine, and the sixth site it is occupied by the water molecule. The sixth site it is occupied by the water molecule. So you should remember, whenever the iron porphyrin ring is there, it is considered as a heme part. It is attached to the 4 nitrogen, but actually it is a octahedral complex, so it has total 6 sites. So the 4 nitrogen, fifth site it is the nitrogen of N-histidine residue, and the sixth site it is occupied by the water molecule, or sometimes it is vacant. And then if you consider what happened if you consider the sixth site it is vacant for coordination, and this part, if you consider, there is a globular part is there. So around this iron porphyrin ring there is a globular part is there. So this is your heme, and globular part is there, therefore it is considered as hemoglobin. So it having 6 sites, so 4 nitrogen, fifth nitrogen of histidine, and the second sixth site is vacant. When this sixth site it is vacant, then this form it is considered as a deoxy form of hemoglobin. Deoxy form of hemoglobin without oxygen, we can say that it is deoxy form. So this is the heme part, and this is a globular part, therefore it is considered as a deoxy hemoglobin without oxygen. So deoxy form of hemoglobin, so without oxygen. And in this case, this Fe, due to this a larger size of Fe, so if you know that the deoxy form, it is a tense state because there is a lot of interaction, that is hydrogen bonding is there, disulfide bonding is there, van der Waal attraction is there, different types of forces is there, and therefore this Fe, it is cannot fit into this cavity. It will away from this cavity, it will shift the position from this center to upward position, and therefore due to the high size, or we can say that this Fe, it is in high spin state, high spin state. So if you consider the deoxy form of hemoglobin, the Fe, it is in high spin state, again it is in +2 oxidation state. You should remember this point, that is whenever we consider the deoxy form of hemoglobin, so let us discuss Fe. It is attached to the 4 nitrogen, the tetrapyrrole ring nitrogen. Again there is a N-histidine residue, 5th site, and the 6th site is vacant. So this is your deoxy form, in which the deoxy form, it is considered as a T state. It is very tense state, there is a lot of tension in the deoxy form, so it is considered as a T state, in which the Fe, it is in +2 oxidation state, and then this Fe is in high spin state. So you should remember this point, it is in high spin state without oxygen, so oxygen is not bind with this deoxy form. So a T state is there, Fe is second high spin state, and this Fe is cannot fit into this cavity of this porphyrin ring, and therefore it will shift its position to upward, or it is we can say that it is lie above the plane of this 4 nitrogen. So whatever the geometry of this complex, it is a square pyramidal geometry, it is a square pyramidal geometry. So you should remember T state, Fe second, high spin, square pyramidal geometry is there. And again if you consider the deoxy form, so we can whenever the oxygen, so let us discuss, when the oxygen is bind with this deoxy form of hemoglobin, deoxy hemoglobin, when O2 molecule is there and it interact with this deoxy form of hemoglobin, N-histidine is there, and there is a O2, then this form, it is considered as the oxyhemoglobin. When oxygen is bind with this Fe, then it is considered as a oxyhemoglobin. Again if you consider this oxygen, it is a strong field ligand, it is a strong field ligand, it is a strong field ligand, and therefore this oxygen, it will takes one electron from this Fe, and it will convert this Fe second into Fe third complex. So no doubt whenever the oxygen is bind, it is a strong field ligand, so there is a pairing of electron, and this Fe second, it is convert into high spin to low spin. When in oxy form, then it is in low spin. But we know that this oxygen, it is act as a electron acceptor, it will takes one electron from this Fe and convert into superoxide form. So you should remember no doubt in some references they gives Fe is present in +2 oxidation state in oxyhemoglobin, no doubt in this case also the Fe is in +2 oxidation state, it is a low spin complex when oxygen is bind. But what happens when this oxygen molecule takes one electron from this Fe, the Fe is converted into Fe third, and whatever this oxygen, it is converted into superoxide form. So you should remember the two forms of oxyhemoglobin. One is the simplest form, that is Fe is in a +2 oxidation state and it is low spin, but another form is there in which the oxygen, if you consider this O2 molecule is there, it is in superoxide form, so it having a negative charge on this O2 molecule. Again the remaining structure is same, N-histidine is there, and in which the oxidation state of this Fe, it is +3 oxidation state. So you should remember, many times the question is asked in CSIR NET and SET exam is that a lot of students get confused between this oxyform hemoglobin. So you should remember, this oxyform hemoglobin, it will present, it having a two form, in which Fe is in +2 oxidation state as well as Fe in +3 oxidation state. Whenever Fe is in +3 oxidation state, then the oxygen in superoxide form. It means the oxygen having a negative charge is there. So this is regarding to the deoxy and oxy form of hemoglobin. So this is all about the reversible binding of protein to a ligand. So in next lecture we will discuss the remaining points of this protein ligand interactions. So at least you should know the hemoglobin, myoglobin, the deoxy, oxy form is there, and how this binding. So there is a reversible binding. It is not irreversible, it is reversible. So when this O2 molecule interact with this hemoglobin, then there is a transport of oxygen from this lungs, from the lungs to the tissue, where the oxygen molecule interact with your myoglobin, and there is a storage for further use. And then again this molecule, the deoxy form, the oxyhemoglobin is converted into deoxy form, and then again it react with your oxygen molecule. So in the next lecture we will discuss the remaining type of interaction between protein and ligand. Thank you.